Let's take a look at transforming some functions here. So here we have an example of a type of function, specifically an absolute value function. And so our absolute value function, we've got a few of them going on here, but this one in blue is the function f of x equals the absolute value of x. And I think from our experience, most of us have seen that. Okay, see the absolute value of x keeps everything positive. Now what happens when we take the absolute value of x and we add 3 to it? Well, everything is going to move up 3. So when we're adding to the outside after we perform the function like this here, we're adding 3. Everything goes up 3. So this 0, 0 is going to go up 3. This point right here, this 1, 1, this c value is going to go up 3 units north. Okay? So everything's going up 3 plus 3. Adding 3 on the outside is going to move it up because remember, the value of a function is the height of a function. So if we take the height of a function and we add to it, it's going to make everything go up. The height goes up. And now, what if we say absolute value of x minus 2? Well, if we do absolute value of x minus 2, that's going to take everything down 2 because the height that we had before when we did absolute value of x here, all these heights are going to be dropped by 2. So when we subtract on the outside, everything goes down 2. All of these points, this point right here goes down 2. And to this point, okay? So the heights are all dropped by 2. Okay, so and this works for any type of function, not just absolute value. So we're kind of just using absolute value as an example right now. Well, what if we take a function and we add a number inside the function? Okay, meaning if we have a function f of x, okay, and we just say let's keep using absolute value of x. Well, what if we take that and we do absolute value of x plus 3? So we're adding something inside the function itself. Well, when we do this plus 3, we take our blue function, which is the graph of f of x, and everything moves left 3. So notice this b value is going left 3. And if you pick a point like this one right here, it's being translated. We call this a translation. It's a slide over to the left. So everything in this blue curve here is moving left 3. Every single point moves left 3. This point moves left 3 to get to the green line. All right, so adding 3 moves left. Now it's kind of weird that adding moves left. It's opposite from what it seems like it should be. One way to make it understand a little bit is think about what do you have to put into that x to make the inside become 0. Well, it's pretty easy to see that we want to put negative 3. So when x is negative 3, the inside acts like 0. And what happened to our original function here when we put a 0 in there? Well, the absolute value of 0 is 0. So negative 3, which is to the left of the origin over here, negative 3 acts like 0. So whatever makes this 0 is what acts like 0. So that kind of shows us that we're to the left 3, okay? Because every time you put a number in here, it automatically gets bumped up 3. Well, if we do the opposite now, if we kind of subtract, if we take f of x, a new f of x, and we make it, let's call it h of x, and we're going to make that x plus, nope, sorry, let's back that up, x minus 2. Okay, well, we should expect the opposite thing here. So when we subtract 2, we get this red graph. Okay, and when we subtract 2, we notice that this blue graph, our original f of x, has moved to the right 2. So everything moves to the right 2. The origin moves to the right 2. This point, which was on the original blue curve, has moved right 2. Everything moves right. Okay? When we subtract 2. Okay, again, it's opposite from what it seems. In this case, subtraction goes right. And you can play that game and say, what can you put in here to make this inside be 0? Well, it's 2. So 2 is that new vertex. So we saw there that when we add and subtract, it moves up and down or left and right when you add and subtract. Those are called translations. Well, now we're going to look at some stretching functions. So let's start with this function right here. F of x equals x to the 5th minus x squared. Now I picked one that was a little different here just so you can kind of see that this works in more complicated functions. Okay, so that is the blue curve right here. That's x to the 5th power minus x squared. And what happens when we take 6 times f of x? Okay, so the computer that I graphed this on now has taken that f of x and multiplied it by 6. Let's go ahead and compute that, and we can see what that is there. So let's do a little bit of algebra. 6 times f of x is just 6 times x to the 5th minus x squared, and distribute that 6x to the 5th minus 6x squared. Okay, so everything's been kind of multiplied by 6. Well, the thing to see here is what has happened to these points. Well, this point right here has kind of been stretched down. Okay, this point right here has been moved down as well. Okay, and as we look at these different points, we can see everything has been stretched away from the x-axis, except for this point right here. Okay, these zeros, we call them, this point, these x-intercepts, they haven't moved at all. This x-intercept here hasn't moved at all, okay, because they're right on the x-axis. But every other point has been stretched away from the x-axis. Okay, so that's what happens there is it stretches vertically. So this is what we call a vertical stretch. Everything gets pulled away from the x-axis. Of course, all that stuff except for 0, 0. Okay, so everything's getting stretched away. It's 6 times farther because remember, this just means here we're multiplying the height of the function, because the value is the height, times 6. So it's 6 times farther away. If this right here, I'm not sure what that is. Let's approximate. If that's like about 0.3. Okay, so this has a distance of 0.3. Well, this distance right here should be 0.3 times 6, which is 1.8. And yeah, that looks like that's about 1.8. That has a y value of 1.8, or specifically negative 1.8. So again, the height is getting stretched 6 times in this case. And if we were to make that a 1/6, well, it would shrink towards the x-axis, okay? All right, well, what if we put a negative number out in front? Well, the simplest negative number is negative 1. So if we have negative 1 times f of x, then what happens is it flips. And here we graph this with a dotted line so we can not get too confused. Here's our function, x to the 5th minus x squared. And if we multiply it by negative, what has happened is we're just taking the y value, because f of x is a y value, and we are making it opposite. Well, when you make a y value opposite, this negative y value bumps up and becomes a positive y value. This positive value here of 2 flips down here and becomes a negative 2. So all the positive heights become negative heights. All the negative lines that we used to have became positive, and the green dotted line here is negative f of x, or more specifically, it's negative times x to the 5th minus x squared, which would be negative x to the 5th plus x squared. So that's what that green line is there. Call that g of x. All right, so putting a negative in front flips it vertically, Putting a number in front is going to stretch it vertically or shrink it. If this was, again, this is 1/6, it would shrink it. So we've added numbers to the inside and outside. We've multiplied numbers outside the function. And what about if we multiply inside the function? Well, if we multiply inside the function, we get a little interesting result. Here is the function, again, f of x equals x to the fifth minus x squared. Don't worry about why the graph is that way. That's what the calculator or the computer says. Great. There's our graph. We'll get into that more in the future. But when we do f of 6x, we get this green little curve there. What in the world is this f of 6x? Let's see if we can figure that out a little bit here. So to find f of 6x, we're going to substitute f of, well, back up here. Let's take the function, which is x to the fifth minus x squared. And everywhere where there's an x, we're going to put 6x. Okay? And we're going to get a pretty large number here. So this is going to be 6 to the fifth, whatever that is, x to the fifth. Got to remember our power rules. That 5 affects both of them. All over 6 squared, x squared. And this turns out to be a pretty big number, 7,776x to the fifth minus 36x squared. Well, I like this example because it's extreme here, because we can see that, man, this is shooting up real fast. But what does this 6 have to do with things? Well, what is happening is this horizontal distance here from the y-axis is 6 times the distance it was. So it is shrunk. Okay, I should say it's 1/6 of the distance. Okay, because it takes a number that's 1/6 as large to make it go up as fast here. Okay, so if you want to make the green graph act the way that 1 does, see 1, when you plug 1 into this original function, you get 0. Well, what do you have to plug into here to make it 0? All you have to plug in is 1/6. So the 1/6 on the green graph is an x-intercept just like 1 is. So every x value is going to be 1/6 of the x value of the original function. All right, so it shrinks. We call this vertical shrink. Everything has shrunk towards the x-axis. And over here, this blue line or blue curve has been shrunk up. Okay, so this particular one is a vertical shrink. Okay, so that's what happens. And the exact opposite is going to happen if we have something like h of x equals f of 1/6 x. If we put 1/6 x where every x is, it's going to be stretched, something like this. Okay, it's going to stretch out real wide like that. So everything's going to move 6 times farther away from the x-axis. Now, what happens if we put a negative inside of the function? Well, if we put a negative inside of the function, all of a sudden, all these negative numbers start acting like positives, and the positive x values start acting like negatives. Because when you put a positive in here, the negative flips it around right away. What this means is we're taking this function, x to the fifth, and we're putting negative x inside of there. And we're putting negative x inside of here. So the moral of the story is this point right here in the blue had a x value of 1.2 or so, and it flips over here. So the green graph is the graph of f of negative x. This one right here, which had an x value of -1, flipped over to the other side. So when we have a negative inside, we get a horizontal flip. Inside gives a horizontal flip. So Everything that happens inside is horizontal. Everything that happens outside is vertical. In the end, our general form looks something like this. F of x equals a. If we multiply out here, this stretches it vertically. If we add out here, this moves it left or right. If we multiply it inside, it stretches it horizontally, opposite from what it seems. If we add in or subtract inside, it moves it left or right. Horizontal inside, vertical stuff on the outside. Quick example, let's find a function of g of x. So here's g of x over here. We want to write that as a transformation of f of x. So we've got to ask ourselves what has happened here. First, let's remember that we know this is the function y equals x squared, and we'll usually be told that in problems like this at this point in the game. So notice this vertex has moved left 5 and up 1. So let's take our function y equals, and we've got x squared normally, but we're moving left 5. So remember, inside here, when we add inside the parentheses, that's what's going to move it left 5. So let's add, because left is addition, subtraction is to the right inside. Always opposite inside the parentheses, opposite of what you would expect. And then it's gone up 1 here, so that up 1 is going to go to the outside. This d value is up or down, and so we've gone up. Now we got to ask ourselves, is it the same shape? Well, here's our normal parabola. We go over 1, 1 squared is 1. Over 2, 2 squared is 4. So there's a point there. But this shape doesn't quite match, because starting from the vertex, we go over 1 and up 2. So what's going on? Well, here, that little kind of slope there is twice as high, twice as steep. So it's going up 2 instead of 1. And if we could check, it's off the charts here, but if we go 2, we'd be going up 8 instead of going up 4. Okay, so it's going up twice as high there. Okay, so everything's being stretched vertically by 2, and that's the a value. There's no horizontal stretch, nothing to worry about there, so we have no b value here, just a vertical. And there's our function there. So we can write it like that. Sometimes it'll be useful also to say this. In general, we can see that g of x is 2 times f of x plus 5 plus 1. So if we couldn't say, if we didn't know that it was x squared, we weren't quite sure, this would be the best that we could say here. Okay, so anyways, but since we know it's x squared, there's our answer. And that's how you do that, moving up, down, left, or right, and shrinking and growing in the vertical direction and inside for the horizontal.